Hi, my name is Ming Yao, and this will be a quick demonstration of some basic ANSYS AIM CFD simulation. The problem I'm going to look at today is a basic flow over a cylinder, which is usually the first simulation anyone does when they start working with computational fluid dynamics. The nice thing about flow over a cylinder is that it's well tested, well understood, and there's actually a lot of interesting phenomena that goes on in the cylinder flow that may be challenging to model unless you have the proper setup. So here we go. We're going to start by defining the geometry. I'm in the ANSYS space claim system. We'll start with a 3 meter gap, maybe 2 meters is fine too. And in this section, we'll make it 8 meters. Let's try that again. So 3 by 8. Okay. We want to exaggerate the downstream section. So let's say the flow goes from the left-hand side to the right-hand side around the cylinder. We expect wake and vortex shedding behind the cylinder. So we want to have enough resolution over here to capture that. So I'm going to move this back to, let's say, 10 meters. I will move this over here like 8. So we shifted my rectangle a little bit to the right-hand side. Actually, let's make this a bit longer, so we can capture plenty of interesting things behind here. This is our first section, and the second section is our larger domain.
The reason we create two domains is to reduce the mesh size so that the simulation runs quickly. The inner domain will be meshed finely, and this allows us to capture accurate physics inside and near the cylinder. The outer domain is meshed with a coarse mesh. This allows us to reduce the mesh count while still maintaining the validity of our boundary condition assumptions.
So I'm making a 30 meter by 60 meter box here. Again, we'll drag this back by, say, 20 meters to 80. Let's do 80, and then we'll do 60 here. So we have flow coming in from upstream here. It's going to flow around the cylinder, and then various vortices, sheddings, and things will happen back here. Maybe I'll move this back a little bit. Let's say it's 65. The exact dimensions don't matter as long as they're fairly large with regard to the cylinder here. So from there we can start creating the geometry. Delete the center because we're only interested in the computation domain. I'm going to pull this out by 1/10 of a millimeter and pull this out by 1/10 of a millimeter. Clicking on the no merge option ensures that I have two solids available. This will be my far field, just so I can differentiate the two.
One of the key meshing controls inside SpaceClaim is this option for shared topology. Having a shared topology means that the different parts will be meshed conformally, which means that the small inner section will share nodes at the interface with the larger outer section.
Okay, so we'll start AIM this way. We're starting AIM 18.2, and we'll point the simulation to our geometry. AIM is a multi-physics platform that allows us to do computational fluid dynamics simulations like this flow over a cylinder, but it also allows us to do structural mechanics, electromagnetics, thermal, and various other types of advanced simulations. So let's go with a fluid flow analysis. We'll start that. We're going to connect to an active CAD session, which is the SpaceClaim geometry I've defined. We're just going to start with a steady state simulation, but we'll try some transient analysis to look at some of the phenomena like vortex shedding later on. So AIM has this guided workflow where we start by importing the geometry. It automatically recognizes I have a SpaceClaim design loaded on my computer, so we bring that model in for an analysis. Meshing here, The default control is, I believe, tetrahedron. So we want this to be a hex model. I want to be a fairly refined one. And we want to find some boundary layers. So we know as the flow speed increases, there will be a significant boundary layer flow around the cylinder. So we select the cylinder here, and we can specify, for example, a first layer thickness. Depending on the velocity, first layer thickness is typically defined using a calculation based on the y plus value, and depending on the maximum velocity you expect, we want a y plus value for turbulent flow of less than 1. So y plus value is also a function of the viscosity of the fluid. In this case, we're using air, which is a fairly inviscid fluid. That results in fairly small y plus value. So we're going to do 2e to the minus 6 meters for a y plus value. For models like this, we need a lot of boundary layers. I'm going to go with, let's say, 50 layers here. Back. And let's take a quick look at the model. I've slid the slider over here to high just to have ANSYS automatically try to generate a finer mesh. So you can see that we have a very well resolved Y plus boundary layer mesh near my cylinder. But the transition here isn't great. I actually want a much more refined mesh in the center section here. So to do that, I can assign some phase sizing for these two surfaces. And I'm going to go with, okay, this is probably far. Let's not do a 1 millimeter. Okay, so that element here shows me the phase sizing that I've applied. So the 1 millimeter mesh size is far too small. Let's try this one. This will be 10 centimeter mesh. So it's much more refined. Probably go even. We should probably increase the number of layers. The other thing we want to make sure is we want to have a few elements to the thickness here. So to do that, we can define edge sizing, where we select the edge here, and we'll specify that we want 2 elements in that edge, along the edge. So there'll be 2 elements there. And let's go back to our boundary layer controls and increase it a little bit to 55 layers. Okay, so that's got 2 layers to the thickness here, and by specifying 55 layers, we're getting close to the point where there's a smooth transition. You want the elements from the boundary layer to be fairly similar to the first layer outside of it, and we still have a fairly large transition here. So let's go with 60 layers. Actually, I think there are some global settings maybe we can change.
Here we're turning off the predefined settings. Predefined settings are default settings that ANSYS selects for our simulation and mesh generation. The growth rate is changed from 1.1 to 1.2. This means that we allow the mesh to grow slightly faster as it transitions from a fine mesh to a coarse mesh.
Okay, so that looks much better. So I've increased the number of elements around my circle to 5-degree arcs, which means every element spans a 5-degree arc of the circle. This causes a fairly refined mesh that grows to pretty much match my 10 centimeter elements around in my inner region. If we look down here, it shows us we have 40,000 nodes, which is a very small model here. So this should enable us to run simulations fairly quickly. Okay. So with this model set up as it is, let's start defining some boundary conditions. First, we want symmetry boundary conditions on both sides of the cut plane. So this is a pseudo 2D simulation. I'm going to put frictionless boundaries or symmetry boundaries on these 2 areas as well. This makes the simulation much simpler. On the outlet side, we want to add an outlet. So this will be 0 gauge pressure outlet, and then we just have to define the inlet of our flow. So if we look into, so one of the goals of the simulation would be to predict the drag on the cylinder. If we do a Google search for drag over cylinder, you can see that's very characteristic. It's always defined based on Reynolds number and coefficient of drag. There is initially a downsloping section, then for a wide range of flows it stays around 1. At around 3 to 500,000 Reynolds number, there's a sudden drop, and then it goes back up again. So we're going to pick a few values in this section and run the simulation, which means we have to figure out what the Reynolds number is. So we could set up, we could do hand calcs and define the velocity, or in the case of AIM, we can specify some equations and named expressions of values. So let's start with some named expressions. So the diameter of my cylinder is 1 meter. The Reynolds number is a function of flow velocity, diameter, and viscosity. Let's go back to my physics section. The material assignment for the gas. So this is air, and we're using the viscosity of this. So we can go in here and copy the value, or we can copy a function. Let's try that. So go back to study, and we'll add a new named expression. So this will be viscosity, and this. Go back to my named expressions. I have diameter, viscosity, so my Reynolds number, and we want to define our desired Reynolds number. So our goal for velocity we're going to start with is a Reynolds number of 100. Reynolds number is dimensionless, so I think that's all we need to do here. So when we have an inlet, I can define this surface as my inlet. And instead of magnitude and direction, I'll just specify directional components. The flow will be in the plus x direction based on this triad here. So my y and z are 0. And here we can specify, create a name expression or value, or we can just type it in directly. So the velocity will be my Reynolds number times viscosity. Oops. Let's try that again. Reynolds number times viscosity divided by the diameter. Let's take a look at my definitions for viscosity. So ANSYS does ensure that the units all make sense here. So let's go to study, named expressions, viscosity.
So the viscosity in the Reynolds number calculation is the kinematic viscosity, which is the absolute viscosity here divided by the density. Since the density of air is about 1, we can just switch the units.
So if we switch to meter square per second, ANSYS will understand the my inlet boundary conditions, and it'll calculate a proper velocity for me. So that's all I need to do for the simulation. On the results side, one of the things we want to monitor is a coefficient of drag. And to do that, we need to monitor we have symmetry, outlet, inlet. We need to find a wall on my cylinder. So I'll add another flow condition called wall here, and call this wall the cylinder. Okay. So the coefficient of drag is the axial force on the cylinder divided by half of rho v squared times the diameter. So let's put that expression into the calculated result. Right, a calculated value, and we'll use a user-defined expression. So this will be my coefficient of drag, so I'll set it to CD. And this will be the sum of force in the x direction, comma, and we need to define the location, which uses a Python command called getBoundary, and getBoundary will be using the @ symbol cylinder, and there's an option of various types of weighting, so we'll do a simple sum of the values. So when I hit enter, you can see that it did calculate that force value without throwing any errors. So this calculates the force. This will be divided by 0.5 times the density, which I can pick directly from the material properties. Let's copy the density here. Going back to results. So 0.5 times the density. The density needs to have square brackets to represent the unit system. Times the velocity squared, which is the equation we provided earlier, or we can measure the velocity. So the inlet velocity is, let's say, the average of velocity in the x direction. Get the boundary at in brackets inlet 1, and we'll also do a simple average here because it should be at the same value. Let's see if that works. So quick check of my names. So this is indeed called inlet 1. Let's see what the error is over here for my coefficient of drag. Oh, I think I just left out a bracket here. Okay. So half times the density times my velocity squared times the diameter of my cylinder move the comma there, and that should be the coefficient of drag. Well, saying that in Python we should use 2 stars to represent that. Now remember, my cylinder here is only a tenth of a meter, so whatever value we get here, we need to divide it by 0.1 meter. And that then should get us a value. So the nice thing about setting these type of expressions is that we can then monitor the expression during the simulation and see how the analysis, what kind of results we get.
The initial simulation was set up with a Reynolds number of 100, which is a very laminar flow. By default, AIM selects a turbulence model, which assumes that the flow is turbulent. This makes convergence difficult for low Reynolds number flows. We're going to switch this to a higher Reynolds number just to get a converged results. Then we'll switch the turbulence model and see the difference in the results. During the simulation, we can monitor both the convergence residuals as well as the coefficient of drag.
Okay, so the simulation is finished. You can review the results here. Click on results and update. It'll calculate all of our results for us. So this is the Reynolds number 200. We can take a look at the velocity. contours as well as a coefficient of drag. So the coefficient of drag is about 1, which is what we'd expect for a simulation like this. Do various other post-processing here. For example, we can select the faces here and look at contours of pressure distribution. So flow over here, you can see that it goes around my cylinder. It's high pressure region. Then we have separation or low pressure region as it goes around the curvature. We can change it from pressure to x directional velocity.
The wake section here behind the cylinder is well resolved. This is why we needed an area of refined mesh behind the cylinder. In addition, notice the rapid increase in velocity near the walls of the cylinder. This is captured by resolving the boundary layer flow with the proper meshing.
And this is needed because by default, ANSYS uses a advanced turbulence model called shear stress transport, which allows us for the explicit resolution of mesh in the boundary layer. So that's one simulation at a Reynolds number of 200 here. Let's go back to my study and we can edit my Reynolds number to, let's do a simulation of 1,000. So based on our graphs, we'd expect 1,000. So we did 1 at 200. Let's do 2,000 here, and then maybe 10,000. So you can try out different flow regimes to see how they respond. Okay. Under physics, you can go ahead and solve the simulation again. So the solver inside AIM is very robust and it tends to converge nicely. So it's done after 85 iterations. And let's take a look at the results here. So it looks similar, except the wake region should be larger. So this brings some interesting effects. If we look into ideas about how the flow should be around a cylinder, as the velocity speed up, we should expect unsteadiness, and vortices should be shedding off at around over 90, Reynolds number of over 90. Now the reason we're getting this type of result is that it's by default we have turbulent modeling turned on, so we can, for example, turn off and force a laminar solution in the physics and run the simulation again.
By turning off the turbulence model, the convergence becomes very difficult. We're picking up a lot of the transient effects in this laminar flow around the cylinder, so both our coefficient of drag as well as our convergence plot oscillates greatly.
So we'll stop the simulation and we'll switch to a transient analysis. Go from steady state to transient or time dependent. For time dependent analysis, ANSYS requires you to assign a time duration. Let's do 1,000 seconds to start out with. And we have to specify some initial conditions. So I think I still have, I'm going to copy that expression from my inlet and specify that as our initial condition. So my inlet velocity will be my initial conditions. It's going to have 0 on Y and Z and 0 static gauge pressure.
The default transient solver inside ANSYS AIM is a huge improvement over the previous techniques available. Previously, users had to manually assign a time step, trying to manually balance between the speed of the simulation as well as convergence and accuracy. ANSYS AIM uses truncation errors to decide on the optimal time step, and it continually modifies that throughout the simulation to ensure that transient effects are captured and the accuracy of the simulation is preserved.
Okay, the simulation is completed. We can take a quick look at the results. And specifically, I want to take a look at the contour velocity values at the end of the 1000 seconds. So we can see some of the vortices that's been shed from my cylinder here. Now the problem is if we look at this, it really hasn't steady. We've only gotten 1 or 2 cycles. So what I can do is I can run this for a bit longer. Going back to physics, let's just add another 200 seconds on top of this. And this will just continue the analysis from where it left off. Okay, so we've ran this for a few more iterations. Now we have some cycles of vortex shedding. So what happens here is that initially it took a period for the flow to stabilize, and at some point some instability has begun. And once the simulation ran for long enough, the instability stabilizes into these periodical oscillatory motion. And this is the type of drag values that we're typically looking for. We can export this as a CSV file and do a lot more post-processing if needed. But let's take a look at the results first. So we'll perform the evaluation for the full range of velocities, and we can take a look at visually in the form of a movie how the flow develops. Okay, so let's move everything out of the way and take a look at how this flow develops. So this just shows you the ability to quickly model a basic CFD simulation, validate it, and switch to a transient simulation if needed. So this is our vector plot. The vector plot here is showing vectors on the entire area, but let's restrict it to the area of interest, just inside this area. And the vectors are too big, so we'll make them smaller. The vectors are often a great way of showing vortices and flows. So let's evaluate all the results here and take a look at the vectors afterwards. Okay. Okay, and that's the end of this demonstration of ANSYS AIM CFD, flow over cylinder. Thank you.